Your lecturer is Dr. Richard Wolfson, the Benjamin F. Whistler Professor of Physics at Middlebury College. Professor Wolfson is an expert at interpreting concepts in physics, climatology, and engineering for the non-specialist. Dr. Wolfson is also the author of several books, including Essential University Physics and Simply Einstein, Relativity Demystified.
So what is this thing, physics? Well, welcome to Lecture 1. And in Lecture 1, I'm going to try to give you a brief answer to what physics is and also to what physics isn't. But really, to answer my question fully, you'll have to go through 60 lectures with me, and at the end, when you've seen Lecture 60 and everything in between, you'll be able to answer much more thoroughly the question, what is physics, and also what isn't physics. But let me give you a quick answer. Physics is the fundamental science. It's the most basic description we have of physical reality. It governs the workings of the universe at really all scales. And in that sense, physics is different from some of the other sciences that tend to be concerned with particular size scales of entities. For example, chemists are concerned largely with molecules. Geologists are concerned largely with planetary-sized things, mountains, continents, earthquakes, things like that. Biologists are concerned with cells, organisms, even whole ecosystems. But for physics, it's the whole gamut. Everything from the tiny subatomic particles called quarks and leptons, which we'll get to much later in the course in more detail, on up to the stars, the galaxies, the clusters of galaxies, and the large-scale structure of the entire universe itself. So we're dealing with a much greater range of scales here with physics. We believe that interactions among the fundamental entities of physics, the quarks, the leptons, the elementary particles that make up all matter, we believe that the interactions among those, which we understand to some extent, give rise to structure at all these scales. So what makes a galaxy is ultimately in some sense traceable to these fundamental entities and how they interact. And part of the theme of this first lecture is trying to understand how and whether that knowledge of the most fundamental entities and their interactions really explains everything else. Some physicists would say yes, some would say no. I'm going to give you my slightly nuanced take on that in a little bit. But let's first take a look at some of these scales of physics. So I've got a diagram here, a little table that sort of suggests some of the kind of scales we're going to be thinking about in this course. And in some lectures, we'll actually cover many of these scales all at once because some of the same physics principles will apply in many different realms. So the subatomic scale, the scale of elementary particles, of nucleons, the protons and neutrons that make up the nucleus, which themselves are composite particles of quarks, for example. The typical size we're talking about here is about 1 femtometer. That's 10 to the minus 15 meters. I'll say a little bit more about math and scientific notation in the next lecture. But for now, let's just hold to that. 10 to the minus 15 is 1 over 1 with 15 zeros after it. These smallest scale objects are things we study with our giant particle accelerators, and the diagram for this particular scale is a picture of a particle collision in the new Large Hadron Collider. We move up next to the atomic and molecular scale, the size scale of atoms and molecules. It's on the order of about 1/10 of a nanometer, 1/10 of a billionth of a meter, 10 to the minus 10 meters to 10 nanometers. So I'm putting about 10 to the minus 9 meters, 1 nanometer as sort of the typical range for that scale. The next scale is one that I probably wouldn't have put in this diagram if I'd been teaching this course 20 or even maybe 10 years ago, and that's the nanotechnology scale. That's the scale of the smallest human-engineered structures. And that scale has gotten so small that it's beginning to overlap with the atomic and molecular scale. I would put the nanotech scale at somewhere between about 1 and 100 nanometers, hence the term nano. Nano means a billionth. So somewhere in the scale between 1 and 100 nanometers, overlapping at the lower end, the atomic and molecular scale, is the nanotech scale. And the picture we see here is a diagram of the chemical structure of a carbon nanotube, a wonderful, newly engineered, large molecular thing which can serve all kinds of useful functions in miniaturized technologies. Next scale I'll mention is the human scale. That's the scale of the everyday world. A typical human is somewhere between 1 and 2 meters tall, so I'll say that scale has a size on the order of about a meter, about how far apart my hands are here. And so human beings, trees, cars, things like that are all at the human scale. Next, we move up to the astronomical scale, the scale of planets, stars, and galaxies, maybe ranging from about a megameter, 10 to the 6 meters, to something on the order of a zettameter. A zettameter is 10 to the 21 meters, and the photograph here is of a galaxy, which might be 100,000 light years across, something on the order of a zettameter. And finally, we go to the cosmological scale, the scale of the largest things in the universe, the large-scale structure, the observable universe itself, at about 10 to the 26 meters. And the picture you see here is a computer simulation of the formation of large-scale structure, larger than galaxies, larger than clusters of galaxies, huge structures that extend across vast extents of the universe, consisting of regions where galaxies have much greater density, and we're trying to understand those. So those are the scales of physics. Now, I'd like to point out one other thing about the scales of physics. In knowing the universe, it's fairly obvious that if I understand how small-scale things like atoms and molecules and quarks and nucleons and so on work, that's going to determine something about how the large-scale things work also. So the smallest scales inform the largest, as in this pictures taken from the previous diagram of the collision in the Large Hadron Collider, leading to an understanding of galaxies and large-scale structure. But surprisingly, perhaps, the opposite is true too. The largest scales also inform the smallest. What we now know about galaxies and clusters of galaxies and the evolution of the universe comes right back and tells us something about the elementary particles and their interactions. And in fact, one of the most fruitful things that's happened in physics in the last 30 to 40 years is a symbiosis of cosmology, the study of the large-scale universe, and particle physics, the study of the very smallest. And we'll see when we get to the final lectures of the course just how that symbiosis works and how we come to understand the large-scale universe, partly because we know about how the particles that make it up work, but we also know something about how those particles work because we're able to see what's going on in the large-scale universe and how it's evolved. So we get to know things both ways. Now, what is the goal of this thing, physics? Well, one goal of this thing, physics, or the ultimate goal of this thing, physics, is a theory that will allow us to explain everything about the entire universe, sometimes called a TOE, or a theory of everything. We aren't there. We don't have one theory that explains everything, but there are physicists who claim we someday will. We will have a theory in which there will be one interaction, one fundamental way the entities that make up the universe at the smallest scales interact, and that will explain everything. Others are not so sure. Right now we know of 3 fundamental interactions, and we think we see how 2 of them might be mergeable, but we really don't have much of an idea of how to merge the third one, which is, in fact, gravity. So whether or not there will be a theory of everything, I don't know. And I am going to be open on that, and when you get to Lecture 60, I'm going to challenge you about a theory of everything. So that is one of our goals, to get to a theory of everything. Now, if we had a theory of everything, there's a philosophical issue that comes up. And the issue is this. If we really understood the interactions of all the elementary particles and how they worked and combined to make other things, would we really understand everything? The reductionist view, a philosophical view that says we can reduce everything to basic physics, would say yes. If you know the Schrödinger equation, or you know Maxwell's equations of electromagnetism, or you know the theory of everything's equation that describes the fundamental interaction, then you know everything there is to know about the universe, and there is nothing else to be said. I'm going to show you a more subtle view, and I want to take a few minutes, a kind of detour before we get into physics itself, to explore this question of reductionism, because I promised at the beginning of this lecture to talk not only about what physics is, but also about what physics isn't. And I'd like to show you why I believe physics is not going to give us the ultimate answer to everything, and why there's plenty of room for other sciences and other realms of study. Physics may explain in some very mechanistic sense how the whole universe works, but I think there are new things it won't let us appreciate. Let me give you an example. Here's a diagram which I'm going to call quark to cat. And again, we'll come back to this much later in the final lectures of the course, talking about the elementary particles, but let me give you a quick introduction. There's an up quark, a down quark, and an electron, and most of matter, ordinary everyday matter, is made of those 3 elementary particles. Quarks combine to make protons and neutrons, which are the building blocks of atomic nuclei. So there's an atomic nucleus. Electrons come swarming in around the nucleus. We're going to study exactly how this works, including rigorously according to the rules of quantum physics much later in the course. But suffice it to say, we get something like this classical picture that everyone has of an atom with electrons whirling around the nucleus. And we understand pretty much the physical interactions that go from the elementary particles to the atom. Atoms join to form molecules. This is the subject largely of chemistry, although we understand the physical principles that make that happen. Molecules join to form cells. We don't know all the details yet, but cell biologists, microbiologists, are really learning rapidly what the molecular mechanisms are that are at work inside the cell to make it operate. So we think the cell is explainable by molecules, and the cells join to make organisms like the cat I've shown here. Maybe it's Schrodinger's famous cat that will come up much later in the course. So here is this diagram going from the quark to the cat. And in some sense, given the rules that make the quarks interact and the electrons interact with the nuclei that are made of quarks, we understand the cat. We know the physics that makes the cat work. But the question I want to ask is, do we really understand the cat? Do we know everything about the cat? And to look at that question a little more philosophically, I want to take a step outside of physics, actually into biology for a moment, and report on an event that occurred in 2010, a very seminal event in biology, at least according to some, and that was the construction of the first artificial cell. It was done by J. Craig Venter and his associates, the people who first sequenced the human genome. And in some sense, it put to rest a question that's been existing for millennia or at least centuries, and that's the question is there something about life that is outside of physics? Is life just something we will never be able to explain with physics? Is there something new that had to come in to make life possible? And here is a quote by Arthur Caplan, a bioethicist at the University of Pennsylvania, on the occasion of this 2010 construction of the first artificial cell, the first synthetic life. And here's what he says. This is entitled The End of Vitalism. Venter and his colleagues have shown that the material world can be manipulated to produce what we recognize as life. They bring an end to a debate that has lasted thousands of years, and then he goes on to say, this discovery is as momentous as the discoveries of Galileo, Copernicus, Darwin, and Einstein, three of the four of them being basically physicists. More than 100 years ago, he goes on, the French philosopher Bergson claimed that life could never be explained mechanistically, nor created by synthesizing molecules. There was a vital force distinguishing the living from the inorganic, and he says Venter's achievement would seem to extinguish the argument that life requires a special force or power to exist. And I would certainly agree. In some sense, the fact that we can synthesize a cell using principles that are ultimately of physics and of chemistry derived from physics and so on means that life is a natural feature of the universe that is made of quarks and electrons. Somehow in those quarks and electrons is the possibility of life. By the way, I think that's a wonderful thing. I don't think that's something that diminishes the wonderfulness of life. And I want to talk about life as one of a number of properties. They're called emergent properties, and they are properties of complicated systems of ultimately the physical particles that make up the universe. But at some level of complexity, those properties become so interesting, so unique, that even though we understand that they come from the particles that are held together by the laws of physics, we can't understand or appreciate them just by thinking about physics. And those properties are called emergent properties. And emergent properties have been characterized as having organization, complexity, and this wonderful term I've put in quotes here, radical novelty. Let me give you a few examples of emergent properties. In physical systems, emergent properties are things like crystal structures. Here's an example. Here's a snowflake. Now, if I look at how a water molecule is put together, I could probably predict that there are going to be certain angles involved when water molecules go together to form crystal structures. And I might even be able to think there will be many, many kinds of those crystal structures. What I will not be able to do is appreciate how beautiful, how diverse, how no snowflake is like any other snowflake, and so on. So there is something new in the organization of the many particles that make a snowflake that I don't think I can appreciate just knowing how quarks and electrons interact. Geological and atmospheric patterns are other examples of emergent properties, and here we see two of them. We see the ripples in a sand dune, and we see the ripples, the regular patterns in clouds. These two look very similar. These are sort of self-organized patterns that came about by the laws of physics acting in the atmospheric gases or in the grains that make up the sand and gravity and so on. And yet they've given us something new, an organization here that we wouldn't have seen in the quarks and the electrons. In some sense, the organization is latent in the quarks and the electrons because we believe all it takes to produce them is quarks and electrons, and yet there's something new here that we need to appreciate at a higher level. In biological systems, there are emergent properties. Life itself is an emergent property. That elephant is a very complex system, and it's like our cat. Even though it's made of quarks and electrons, I don't think we can appreciate the elephant without looking at it from a very different perspective, the perspective of the biology of organisms, for example, or the ecology of the elephant in relation to its surroundings. Social organization is certainly an emergent property. There's a school of fish. There's a city. These are both social organizations of individual organisms. They themselves could not be predicted from quarks and electrons, maybe not even from knowing the individual properties of the organisms themselves. And finally, what I think is certainly the most intriguing, perhaps the most advanced example of an emergent property is consciousness. And I'm representing consciousness by this wonderful symbol, which will come back to us in the very last lecture. It's a symbol built by John Archibald Wheeler, one of the famous physicists of the 20th century who died in 2008. And he's got this U for universe. The fact that the universe starts out narrow at the right, turns around and evolves thicker and thicker is a sense that the universe is evolving, and it's evolving more and more complexity. And the most complex thing it evolves is consciousness. And then this big I represents consciousness staring back at the beginning of the universe and appreciating what's going on. Wow. So I think a universe in which we talk about emergent properties is actually a much more interesting universe than one in which we would just say, oh, there's quarks and electrons, now we understand it all. And one thing that universe does is it gives us plenty of room for sciences other than physics. Physics is not the be-all and end-all. It is the most fundamental science. It covers the grandest range of scales. It, in some very simple reductionist sense, explains everything that happens. But once you recognize the existence of these emergent properties, you need the other sciences, you need the social sciences, you need history, you need all the rest of it. Physics is not the be-all and end-all, even though it is the fundamental science. Well, enough of telling you what physics isn't. Let me tell you what physics is, because even though physics does not explain all these emergent properties, it does explain a lot. Here's a collage of things that suggest what kinds of phenomena physics can explain. You see phenomena involving a medical diagnosis, somebody going into an MRI scanner. You see the sun. We understand the eruptive outbursts of the sun. That, by the way, is is my field of research. We understand the behavior of light. Here's an astronaut upside down, but not really upside down because there's no up and down in space. We'll come to find out why. There's somebody's smartphone. There's an iceberg floating with 90% of it below the water. Why does that happen? There's a high jumper going over the bar, but the high jumper in some interesting sense isn't really going over the bar. Here's a beautiful bridge in Spain that looks like it should tip over, but it doesn't. Why not? Principles of physics help it not tip over. There's the Earth as seen from the moon. Orbital mechanics explains how that picture got taken. Boy, that's in some sense an emergent property too, that wonderful appreciation we have of that little blue dot. Physics explains how that picture was taken, how the photograph was made, how the spacecraft was launched, how the spacecraft is orbiting the moon, how the moon is orbiting the Earth, but it doesn't explain the emotional impact of that picture on us any more than making the cat out of quarks explains our reaction to the cat, our affection for it, our emotional reaction to the cat. There's an airplane flying, there's an asteroid hitting a planet, a deadly thing for Earth if it happens in our time. There's a giant crane picking up scrap metal. There's somebody getting eye surgery, the great circulation patterns of Earth's atmosphere, lightning, some electronics, a power line, a dancer spinning, a car going around a curve. These are all examples of physics. Somebody going through a scanner, a bad thing, a thermonuclear explosion, a nano photograph, somebody shooting a basketball. All these are examples of physics, and physics explains all those things. So physics explains a lot, and this course is going to take us through a great many of the kinds of things you see in this collage, and you're going to come out the other end not just being told how they work, but understanding in a deeper sense how they work, because this course is going to go beyond just the conceptual physics course where the professor kind of tells you what there is. We're going to actually look at these things using a little bit of mathematics, by the way, that will help us to understand more deeply and fundamentally how all these phenomena work and how they arise. Now, to do that, we're going to divide physics into a number of realms. Physics is a unified description of physical reality, but it's convenient for historical development reasons, for practical applications, and because of our still incomplete knowledge, for example, gravity and quantum physics are not yet reconcilable, it's convenient to divide physics into realms, but that division is ultimately somewhat arbitrary. So let me give you a sense of what these realms are going to be. Physics is the fundamental science. That's really what there is for us in this course. But we're going to divide this conveniently into, first of all, Newtonian mechanics, the description of motion as given to us by Isaac Newton, and used still today. Even though this is hundreds of years old, Newtonian mechanics governs to a very, very accurate extent much of what happens in the world of everyday size phenomena. We will then take Newtonian mechanics and we'll extend it to more complicated systems of lots and lots and lots of particles that undergo wave-type motion or back-and-forth oscillation motion, or the motions of fluids, gases, and liquids that themselves contain so many particles we couldn't apply Newtonian physics to the individual particles. The same is true for the phenomena involving heat. Phenomena related to the physics fields of thermodynamics and statistical mechanics, that comprises our third realm, and we will come to see how those phenomena are largely grounded, again, in Newtonian physics. We'll then look at a big, important area of physics, electricity and magnetism, which will become for us merged to be electromagnetism. We'll look at optics, really a branch of electromagnetism, and then we'll look at what I call modern physics, kind of a misnomer, because it's the physics that's been around since about the year 1900, and particularly we'll look at the theory of relativity and quantum physics, two of the big radical ideas of modern physics. So those are the realms of physics we're going to look at. How are we going to look at them? Well, in a variety of ways. We're going to look at them with regular lectures. We're going to look at them with lots of demonstrations. Physics is about the real world, and I'm going to do demonstrations to kind of show you how physics works. So, for example, in mechanics, we'll figure out how gravity works by dropping a ball and with an electronic sensor simultaneously plotting a graph of its motion, and we'll analyze that motion. We'll go to exotic places. To understand the concept of weight, to really understand that concept, we're going to go into an elevator and do some measurements in there. Then you'll come out of that clip really understanding how weight works and what weight really means. I'm going to whirl a bucket of water around over my head. Why doesn't the water come out? Well, that's kind of a mundane experiment. Easy experiment. Doesn't take a physicist to do that. But understanding why the water doesn't come out also explains why you don't fall out when you go around a loop-the-loop roller coaster. And more significantly, perhaps, it explains why satellites don't fall to Earth or why the moon doesn't come crashing down to Earth, once you understand the basic principles behind that whirling bucket. Circular motion, like the whirling bucket and more complicated circular motion, is really replete with sort of fascinating and sometimes unexpected results. And this example of a bicycle wheel gyroscope spinning which way and that way, and I'm sitting on a rotating stool. I'm going to show you some of the surprising results that come in mechanics when you talk about rotating objects. We'll move on to oscillations, waves, and fluids, that next realm. And by the way, the course will be divided into major sections that are based on these individual realms of physics. I'm going to show you a Doppler rocket, a little rocket that I'll whirl around over my head. It's emitting a sound, but the sound keeps changing. And that is a metaphor, if you will, for police radar, for the Doppler radar that's used to look for intense storms, thunderstorms, tornadoes, things like that. And it's even kind of a metaphor for our understanding that we live in an expanding, evolving universe. We'll look at waves. We'll look at standing waves on strings. These are exactly like the waves that stand on a violin string or a piano string to make music, but also they're like waves of something, we don't know quite what, that stand to make quantum mechanical systems have energy levels that are discrete and quantized and just can't have any arbitrary level. So something as simple as musical instruments also has profound implications for quantum physics. We'll look at the physics of fluids. so-called Bernoulli effect, which has a lot to do with the flight of airplanes, the curved balls in baseballs, and a host of other phenomena, including how blood flows through your arteries. We will also be including in what we do here math as a language of physics. And as I move to thermodynamics and statistical mechanics, one thing I'll do there, for example, is to calculate the temperature of the sun. Very important quantity, and a quantity that's going to come up again and again and again in this course. And we will be using a large screen monitor that will usually be on the set here, and I'll use it as kind of a blackboard and do mathematical derivations. And it's in that mathematics. We're not going to use math all the time, and we're not going to use it real heavily, but we're going to use it enough to get at the fundamentals so I don't have to tell you, oh, this is true. I'm going to say, here's a fundamental principle, and it follows. And you can see how it follows that this is true. So we'll be using that big screen to do mathematical calculations, including, for example, the temperature of the sun. I'll be looking at liquid nitrogen, one of the coldest things we can easily get our hands on, and how it affects matter. I'm going to look at the behavior of gases with an almost explosive effect, how a diesel engine works, basically. A metaphor for a diesel engine is simply causing an ignition of, in this case, a piece of Kleenex at the bottom of a glass tube as it's compressed very rapidly. I'll even beat some eggs for you to show you a metaphor for entropy and chaos. We'll move on to electromagnetism. You associate sparks with electricity and magnetism, and you won't be disappointed. We'll also understand how those sparks arise from releasing stored electrical energy in devices called capacitors, a factor that actually temporarily vaporizes the steel on the screwdriver I'm showing you here. We'll see where all our electricity comes from, namely electric generators. We'll see how electromagnetic technology is used for information storage. What happens when you swipe a credit card? Well, we'll take a look at that, and we'll see actual data coming from the swipe of that card appearing simultaneously on a screen. We'll understand a very basic principle of electromagnetism from that. We'll go on to optics. Optics, a branch of electromagnetism, follows from electromagnetism, but originally a subject all of its own, so we'll treat it as a separate realm. We'll look at a number of phenomena. For example, total internal reflection, something a little bit surprising perhaps that happens when light is incident from inside a material like glass onto an interface with a material like air that has less effect on the light. Although that sounds like a pretty trivial thing, that's the basis of optical fibers, which carry most of our communications today. Every time you send an email, I guarantee you it's going out over at least some of its journey, most of its journey, in fact, on optical fibers that work by this phenomenon of total internal reflection. We'll look at image formation by mirrors and by lenses and see how optical systems work and how we can correct your eyes if they aren't seeing too clearly and things like that. And finally, we'll move on to modern physics. Modern physics, I'll have fewer demonstrations because modern physics involves a lot of sophisticated high-energy accelerators, and we're probing into things like the structure of the atom and the structure of elementary particles. I can't do that here in the studio for the great courses. So we will be relying more on visuals and some derivations, for example, trying to understand relativity theory with a mathematical derivation using high school algebra that tells us that time can't be the same in two different frames of reference. Or we'll look at analogies, like a vibrating loop, which develops standing waves, like those ones I talked about for a long string or a piano string, but that are metaphors, if you will, for the allowed states of an electron in an atom. So we're going to see a lot of demonstrations, we're going to see some mathematics, and we're going to come to understand the basic principles of physics and how they explain a whole host of both natural and technological phenomena, and more importantly, how they lay the fundamental groundwork for our understanding of the entire universe. Now, before we start into physics, one more thing is going to happen. I have the course divided into these sections, but the first section consists of the first two lectures. I'll call it section 0 because we haven't really gotten into physics. And before we start, I'm going to spend one lecture talking about the languages of physics, because I find, as somebody who's taught introductory physics to thousands of students, that not understanding language is one of the biggest impediments to really getting a thorough grasp of physics. And I say languages plural, because words are really important in physics. They're more important than the other language. That other language is also important, though, and that's mathematics. So before we get started on the actual physics, we're going to move in the next lecture to look at the languages of physics, the words, and the mathematics we use to describe physical reality.